It's 225 million kilometers away. It drives across alien terrain, dodges rocks, survives planet-engulfing dust storms, and sends selfies from another world. But how does a Mars rover actually work? Today, we'll break down the anatomy, intelligence, and engineering behind one of humanity's greatest robotic explorers. Why rovers? To understand the marvel of a rover, we first have to ask, why build a robot on wheels to explore another planet? For decades, our first robotic emissaries were stationary landers. These machines, like the Viking landers of the 1970s, provided invaluable but highly localized data. They could only study what was within reach of their robotic arms. It was like visiting a new continent but never leaving the airport. Rovers changed everything. By adding mobility, we granted our robotic explorers the freedom to investigate vast landscapes, follow geological clues, and adapt to discoveries in real time. A rover isn't just a lander with wheels, it's a mobile geological field agent. Rovers can traverse kilometers of territory, climb hills, and navigate canyons, covering far more ground than any stationary platform ever could. This mobility allows them to hunt for the most scientifically compelling targets, adapting their mission based on the very terrain they uncover. Anatomy of a rover. At its core, a rover is a marvel of complex systems integration, a self-contained laboratory designed to withstand one of the harshest environments in the solar system. The central chassis, or the rover's body, is an armored box that serves as its warm electronics box. This heavily insulated structure protects the rover's brain, its sophisticated onboard computers, memory, and sensitive electronics from the extreme temperature swings on Mars, which can plummet to below -100 degrees Celsius at night. It's the core of the rover's nervous system, shielded from the brutal cold and harmful radiation of the Martian surface. Extending from this body is the robotic arm, a multi-jointed appendage that is the rover's primary tool for direct interaction with its environment. This arm is an engineering masterpiece, mimicking the articulation of a human shoulder, elbow, and wrist. It can pivot, extend, and position a turret of scientific instruments with millimeter precision. This allows the rover to drill into rocks, analyze their chemical composition up close, and even collect samples. Without this arm, the rover would be a passive observer. With it, it becomes an active, hands-on scientist capable of performing complex geological field work millions of kilometers from home. Towering above the body is the mast, which acts as the rover's head and neck. Atop this mast sit the eyes of the rover, a suite of high-resolution cameras that provide stunning panoramic views of the landscape. These cameras are not just for taking pretty pictures. They are crucial for navigation, geological context, and mission planning. They allow scientists and engineers back on Earth to see what the rover sees, helping them identify points of interest and plot a safe path forward. The mast can be pointed in any direction, giving the rover a 360-degree perspective of its alien surroundings. Of course, a rover wouldn't be a rover without its wheels. These aren't just ordinary tires. They are specially engineered for the unique challenges of the Martian terrain. NASA's iconic 6-wheel rocker bogie suspension system, used on rovers from Sojourner to Perseverance, is a design triumph. This system allows the rover to keep all 6 wheels in contact with the ground, even when climbing over rocks as large as the wheels themselves. It distributes the rover's weight evenly, ensuring stability and traction on loose sand and treacherous, rocky slopes. The wheels themselves are made of durable aluminum, with cleats providing grip, and have been designed to withstand the unforgiving, sharp-edged rocks that litter the Martian surface. How rovers think. A Mars rover is more than just a remote-controlled car. It's a thinking machine with a remarkable degree of autonomy. While mission planners on Earth set the overall goals, the rover makes many of its own driving decisions. This is a necessity born of distance. The time delay for a command to travel from Earth to Mars can be up to 20 minutes, making real-time joystick control impossible. To navigate this challenge, rovers are equipped with powerful onboard computers that process vast amounts of data from their surroundings. This autonomous navigation, or autonave, is one of the rover's most critical functions. Hazard avoidance cameras, or HazCams, mounted on the front and back of the rover constantly create 3D maps of the terrain directly ahead. The rover's AI software analyzes these maps to identify potential dangers like large rocks, steep slopes, or deep sand traps. It then computes hundreds of possible paths and selects the safest and most efficient route to its designated target. More advanced systems, like the terrain relative navigation used by the Perseverance rover during its landing, allow the rover to compare live camera images with onboard orbital maps to determine its exact location with unprecedented accuracy. This smart driving allows the rover to cover more ground safely and efficiently than if it had to wait for every single command from Earth. Power and communication. To power all this thinking, moving, and science, a rover needs a reliable and long-lasting energy source. Early missions like Spirit and Opportunity relied on solar panels. These panels were highly effective, but their performance was dependent on sunlight. Their power output would decrease during Martian winter and could be severely compromised by dust storms that coat the panels in a fine layer of red grit. To overcome this limitation, larger, more modern rovers like Curiosity and Perseverance utilize a nuclear power source called a multi-mission radioisotope thermoelectric generator, or RTG. This RTG is essentially a nuclear battery. It contains plutonium-238, a non-fissile isotope that naturally decays and releases a steady amount of heat. This heat is converted directly into electricity by a set of thermocouples, providing a continuous and reliable flow of power for over a decade. The RTG makes the rover immune to dust storms, seasonal changes, and the time of day, allowing it to operate its instruments and heaters even in the freezing dark of the Martian night. For communication, rovers use a combination of antennas. A low-gain antenna can receive signals from all directions but is slow, while a high-gain antenna can send and receive large volumes of data but must be pointed precisely at Earth. To make this process more efficient, rovers often relay their data through Mars orbiters, which act as powerful intermediaries, transmitting the information back to Earth at much higher rates. Science tools and experiments. The ultimate purpose of a rover is science, and each one is equipped with a sophisticated suite of instruments designed to answer fundamental questions about Mars. These are not just cameras and sensors. They are miniaturized geological and chemical laboratories. Spectrometers analyze the composition of rocks and soil by measuring how they interact with light. Drills and abrasion tools expose the interior of rocks, revealing textures and minerals untouched by the harsh surface environment. On board the Perseverance rover, instruments like Sherlock and PIXL use ultraviolet lasers and X-rays to map organic molecules and elemental composition at a microscopic scale. Another instrument, MOXIE, is a technology demonstration designed to produce oxygen from the carbon dioxide-rich Martian atmosphere, a critical step for future human exploration. The Curiosity rover carries a powerful instrument called ChemCam, which fires a laser at rocks from up to 7 meters away. The laser vaporizes a tiny amount of the rock, creating a glowing plasma. By analyzing the light from this plasma, ChemCam can determine the rock's elemental composition almost instantly. This ability to perform rapid, remote chemical analysis allows the science team to quickly survey the landscape and decide which targets are worthy of a closer look with the rover's arm-mounted instruments. What rovers have found? Through these incredible tools, rovers have revolutionized our understanding of the Red Planet. They have provided definitive evidence of Mars's watery past, discovering ancient river beds, deltas, and lake beds. They have found that Mars once had all the necessary chemical ingredients for life, including organic molecules, the carbon-based building blocks of life as we know it. Curiosity's exploration of Gale Crater revealed clay minerals and sulfates, which form in the presence of water, confirming that the crater was once a long-lasting habitable lake environment. Now, Perseverance is taking the next monumental step in the search for past life. It is carefully drilling and collecting rock core samples, sealing them in pristine tubes, and depositing them in a designated cache on the surface. These samples are slated to be picked up by a future mission and returned to Earth, where our most powerful laboratories can analyze them for definitive signs of ancient Martian life. Summary: from their robust wheels to their intelligent minds, Mars rovers represent the pinnacle of robotic exploration. They are proxies on another world, extending our senses across the vastness of space. Each kilometer they drive, each rock they analyze, and each image they send back adds another piece to the puzzle of Mars's history and its potential for life. These machines aren't just exploring Mars, they're preparing it for us.